Welcome to another explainer. Today, we're doing something really cool. We are tracing the entire life cycle of digital data. We're following it from its raw binary birth all the way to its final interaction with advanced artificial intelligence. We're going to decode exactly how these computer science systems operate, literally from the ground up.
Right, let's take a quick look at the roadmap for today. We're going to hit data representation, then hardware and transmission, move into software systems, tackle security threats, and finally wrap things up with AI and automation.
Okay, kicking things off with data representation. Before computers can even think about talking to each other, we have to understand how they actually identify themselves.
So, before a device can communicate, it needs an identity, right? The absolutely crucial point here is that your MAC address is your hardware's unique, permanent, physical fingerprint. It's usually written out in this hexadecimal format, something like 00-1C-B3 and so on. And you really have to contrast this with an IP address. An IP address is honestly just a temporary name tag given to your device when it logs onto a specific network. But that MAC address, that stays with the hardware forever.
Now, to handle all the massive amounts of data these devices generate, we have to compress it. For text or supercritical data, we absolutely rely on lossless compression, like run-length encoding or RLE. It basically compresses data by finding repeating patterns and encoding them mathematically so literally nothing is lost. But for stuff like music and photos, we use lossy compression, think MP3s and JPEGs. This method permanently deletes the tiny bits of data that our human senses can't easily detect anyway. It drastically shrinks the file size, but yeah, that original raw quality is gone for good. Moving right along. Now that our data actually exists and is packaged up efficiently, let's look at how it physically moves across different channels and components. So, data flows across physical wires or wireless channels in basically three main ways. Think of simplex as a one-way street. Data is only ever going in one direction. Then you've got half-duplex, which is kind of like a walkie-talkie. Data can flow in both directions, but you have to take turns. You can't talk over each other. And full duplex, that's just your regular two-way telephone call, where data flows freely in both directions at the exact same time. But you know what happens when data crashes on that digital street? Enter the automatic repeat request, or ARQ system. When data is sent out, it includes an error detection code, like a CRC, a cyclic redundancy check. If the receiving end detects any corruption at all, it shoots back a negative acknowledgement, basically saying, hey, send that again. And if the sender hears absolutely nothing, well, a timeout occurs and the data is just automatically retransmitted. It's this incredibly strict logic loop designed to ensure every single packet arrives safely. When that data finally makes it to a computer, it's going to live in one of two primary memory spaces. First up is RAM, random access memory. It's volatile, meaning it basically has amnesia and forgets everything the second the power is turned off. But it is the incredibly fast, temporary working brain of the computer. On the flip side, there's ROM, read-only memory. This is non-volatile and permanent. It holds those fundamental startup instructions, like your BIOS, locked safely away where they can't be accidentally messed with. And seeing how this translates into physical hardware is actually fascinating. Take a look at the difference between a DVD and a Blu-ray disc. Just by swapping from a red laser to a blue laser, the wavelength shrinks from 650 nanometers down to just 405. That one simple shift in light physics allows for a much tighter track pitch on the disc itself, which means you can cram vastly more information onto the exact same sized piece of plastic. Pretty wild, right? Of course, all this hardware we just talked about is essentially a very expensive paperweight without the software needed to translate human commands into machine action. So, to get the hardware to actually do anything, code has to be translated. An assembler handles the low-level, machine-adjacent stuff, but for high-level, human-readable code, we use either compilers or interpreters. The real difference here is that an interpreter translates and executes the code line by line, which is absolutely perfect for live editing and finding errors on the fly. A compiler, however, translates the whole batch all at once, spitting out a permanent, fast-running, executable file, even if it makes live debugging a bit more of a headache. Orchestrating all of these translations and applications is the operating system. It's basically the ultimate invisible manager. It handles memory, constantly shuffling data back and forth between your RAM and the hard drive. It handles user accounts, keeping everyone's files totally separate and private. It manages security, and crucially, it facilitates hardware communication by using specific device drivers to talk to exactly whatever you decide to plug into your computer. But here's the catch. As data moves through these complex software systems and out across vast global networks, it becomes highly vulnerable. Let's talk about security. It's really important to realize that malicious software isn't just one big generic blob of viruses. They all have highly specific intents. A worm, for example, is a standalone program that actively hunts around for weak network security so it can replicate itself. A Trojan horse is totally different. It disguises itself as a legitimate utility, essentially tricking you into opening the gates for malicious code. Adware just annoys you by flooding your screen with pop-ups, while ransomware literally encrypts your data, holding your own files hostage until you pay up.
And we really need to contrast these two attacks because they get confused all the time. Phishing with a PH and farming also with a PH. Phishing is purely social engineering. It baits you with a fake email, hoping you'll panic, click a bad link, and hand over your passwords voluntarily. Farming is way more insidious. It actually attacks the system itself, using malicious code or DNS poisoning to automatically redirect your browser to a fake website, even if you type the web address perfectly. You literally don't even have to make a mistake for farming to catch you.
Then there's the brute force method, known as a DDoS attack, or distributed denial of service. Instead of trying to sneak in and steal data quietly, a DDoS just clogs the network pipes. It overloads a server with so much garbage, spammy data that legitimate traffic can't get through at all. Just imagine a billion fake cars entering a highway all at once. The real commuters are completely gridlocked. Mitigating this takes heavy-duty firewalls and highly responsive network filters to sort the real traffic from the fake. Having traversed the networks, processed the code, and hopefully survived the security threats, we finally arrive at the ultimate frontier, systems designed to make complex decisions entirely without us. If we pop the hood on an expert system, we see an attempt to replicate actual human expertise. It combines a massive knowledge base, which is just a huge repository of facts, with a rules base containing logical if-then inferences. An inference engine then steps in as the brain, matching whatever the user inputs against those rules and facts to solve incredibly complex problems. We're talking things like diagnosing rare diseases or prospecting for natural resources. But machine learning takes this a giant step further. Rather than just following a rigid, pre-programmed set of rules like an expert system does, machine learning algorithms are trained. The system actively ingests massive amounts of data, learns from its past experiences, and actually adapts. It literally teaches itself to independently solve completely new, unseen problems without ever needing a human to write a specific rule for it. And today, we're actively taking these smart systems and using them to automate our physical world. Now, the pros are undeniable. Lightning-fast responses, wildly precise monitoring, and the ability to operate safely 24/7 in environments that would be way too dangerous for humans. But we have to acknowledge the cons too. There's a massive initial setup cost, and as we just saw, they are highly vulnerable to hacking. Crucially, on a societal level, there is a very real threat of deskilling the human workforce as AI seamlessly takes over complex manual tasks. So, to wrap this all up, we've built an absolutely incredible digital pipeline, starting from a single hexadecimal MAC address all the way up to completely autonomous robots. But as these machines learn to run this entire journey themselves, we really have to stop and ask, are we engineering our own obsolescence? It's a huge question and something to think about the next time you interact with any automated system. Thanks for joining me on this explainer, guys. Keep learning and stay curious.